So we start our seminar on biomechanics, and today's presentation is called CFD study on the airflow fields and particle deposition in the human respiratory airway. And the presenter is Associate Professor Xinguang Cui from Huazhong University of Science and Technology. And please.
Yeah, thank you. And thank you very much for the nice introduction from Alex. And it's really my it's my pleasure to introduce my research work to you. In fact, I start to work in this field from 2008 to 2012, when I was studying in the University of Heidelberg, and this is somehow related to my PhD thesis. And that work was focused on the array, but afterwards I worked in some years in United States, and in 2019 I come back to China, and I built my own group and my lab is lab of respiratory multiphase flows, and in my group we focus on research multi-scale particle transport and deposition in the respiratory system. It not only includes the particle deposition, it will also study the particle clearance on the by the RV, and by the markers or by the dynamic motion of the cylinder, and also has in direction one direction to research the particle clouds the surface of the PS surface. What I say? Yeah, the PS surface, the surface of the our radar sac, and also we also did some work use CFD PKPV to study the how particles distribution in the whole body. And but today I will only focus on the CFD study on the airflow field and the particle deposition. And this is the first stage for the particle entering into the human body. And in this work, I will give you more background on the research status and a little bit on the research method, and then afterwards I will introduce the research work.
I'm sorry. We see only first slide. Could you turn, please?
Okay. Sorry.
Please. Yeah. So
yes, maybe I try. Yeah, I think let me try again. What to say? Yeah. Maybe I try again.
It was okay. We saw your screen.
Yeah, maybe. Yeah, maybe. Yeah, let's try again. Yeah. I do the whole.
Okay.
Can you say it now?
So yes, please turn yes.
Yeah.
Left the left button. Okay. We can see. Please hide. Click on hide. New big blue button and hide.
Oh, it's okay now.
No, it was okay. So please. It was okay. Yes, it was okay. Could you please return to Microsoft PowerPoint? Yes, and turn presentation mode. Okay.
Yes.
And you can see here the title.
Can you say?
Yes, we see when you click on slides. And please, we new big blue button to PSTU rule, and please click hide. New big blue button. Can you see new big blue button? And please click hide. Yes, here. And
okay, this one.
yes, this one, and you should click blue.
This
Okay,
one.
hide. Yeah, that's nice. Yeah.
Yes.
Perfect.
Thank you, sir. Anyway, and then I think that I will try my best to introduce more about the research background. And I think the human respiration is very important because if without food, we can maybe live for a month. And without water, maybe we could live in 1 week. But if without the air, maybe we'll only live for 1 hour. So the respiration is so important for us to live in the world. And in fact, I think one big background is I think the respiratory infectious disease. You know, right? Other people know the COVID-19 2019 pandemic. So in fact, it has taken a lot of doctors to our society and our health and the economy. And there are about 800 million people has been affected. It's about 800 million people was infected, and it costs about more than 7 million people to die. And then, so I think in the future there will be more, definitely the more disease like COVID-19, and it will come back again. And then we need to do something to learn how does it transmits between the people. And then it's very important for us to learn about how the virus transport and deposition in the lung system. So, and I think it's always right. There's some toxic matters in our living environment, and in fact, before the COVID-19, and the motivation for us to learn the particle deposit in the human respiratory system is the air pollution, because it could cost about 4 million premature deaths globally, and it may reduce to about it can also reduce our living years, and then it also could take a lot of disease. And we always need to face the threat from the air pollution. Then we need to know how this air pollution toxic particles deposit in the in our respiratory system. And then another third one is that, and for in fact the for the toxic particle to deposit inside our lung system, and it could induce the damage, health damage for almost our organs. For example, lungs, blood, and cardiovascular system, brain, heart, and reproduction. Because these particles are very fine, and for the particles less than 10 micrometer, and they can go inside our human body, and then they can go with our blood blood circulation from the lung to other sites, for example, the brain. In fact, the air pollution not only that in fact impacts our health, and it also impacts our intelligence because it will destroy our nerves. And then also, in fact, there's also other motivations. For example, there's different kind of disease, for example, COPD and asthma. And we don't know the reasons. And if we know how the air flows inside of the respiratory tract, then we may know the reasons, and then we can know how to treat this kind of disease. And also, in fact, the inhaled drugs, and it's also another motivation because the lung has a very large surface, and then when we deliver the drugs through the mouth inside the lung, and then we will and then the drugs are easy to take into our body, and also it could save the dose. Then it has less side effects. And it's yes. And then, in fact, the market of the inhaled drugs is very big. It's billions, yes, billions dollars, yes. And in fact, the inhaled drug is more it's more researched in the United States, and in China, we learn it more from the side of the air pollution. But recently, in China, in some drug factory, and they also try to develop the inhaled drugs. And another unit for the vaccine. So for the vaccine of the COVID-19, and there's some inhaled vaccine. And also for the in fact, this is not about the particle, but it's about the air flow dynamics in the airway. For example, there's some people it has the disease of OSA, and this kind of disease. I'm sorry, I forgot the full name. And when you sleep, when the people sleeps, and the airway collapse, and then the people cannot breathe. But in fact, we don't know exactly the reason. But the CFD can help us to know some of the reason, and by analyzing the washer stress, the pressure, and the airflow structure. And in fact, in this area for the particle in the human respiratory system, we have maybe three main motivations. One is the virus transport, another is the environment air pollution, and the third one is the inhaled drugs. And for us, we don't want to the air pollution go inside the human body, but in another way, it also blocks the drugs into the respiratory system. And there's three sides of important questions we need to answer. One is we need to, in fact, in the 70 area, I'm not sure whether you know it. At first, we need to have a geometry. We need to have the geometry. then we need to rebuild the respiratory the geometry of the respiratory tract, and then we need to get the shorter one. But for the lungs, it's very complex. It has millions of small tracts, and it has, I think, maybe 1,000 millions of sacs, alveolar sacs. And this is, and it's in fact, and also for the because the alveolar wall is alveolar surface, it's also it's a physiological somehow physiology, and then it's it's humidity, and it has also temperature transfer. Then in fact, it's very hard to get a realistic geometry model, and this is one big challenge. Another challenge is that we need to get the suitable flow, but in fact, the flow inside of the respiratory airway is transfers from lamina to the turbulence. And this kind of model, even in a tube, the flow, even it's in a tubular networks, it's very hard to know their characteristics. And the third challenge is we need to know the physical and chemical properties of the particles that we study. And in fact, for some particles, it has very complex properties. For example, the lunar dust. And but in fact, currently, we in most cases we assumes that the particle is sphere. And in fact, for all the research, maybe it can assign to these three size. Yeah. And then, in fact, in the group, in the world, I think still we focus, we see more people in the United States and Europe, and they have did very good works. For Professor Knister and his lab in the NCSU, and he has many publications in here in this area. But and he focused on the whole modeling, direct drug delivery, and his student, his PhD student, Landis, Professor Landis, and he's in the VCU, and in fact his research is only more focused on the nodal to lung drug delivery. In fact, another professor is he's in CBU, and he did some research. Recently, he did some research on the flow structure, and also did some physics. And he has some works has published in the physics of fluid. And Professor Finlay in Canada, and he did a lot of work on the experimental study, and he more focused on the children. And Miss Feng is a young professor, and he has hold the what I say, he has hold the opportunity of COVID 1920. 19, I heard from my friend Light, he has got some fundings during the period of this COVID 2019 event. And he also has some publications in this area recently. And in fact, for the physics, for people to learn the physics of the flow in the respiratory system, I think this professor in Stanford for the university, he did many great work to study the physics. And although recently Professor Xi and Professor Feng also tried to do some more work to analyze the physics of the flow in the respiratory system, but I don't think they have very great work as this professor in Stanford and also in the Johns Hopkins University. And the last one is my supervisor in Germany. And we start from together to study the unsteadiness of the flow in the upper way. And in fact, I didn't publish so many papers during my PhD study. And I published more papers recently. And in fact, for the let's start from the geometry. And in fact, these three geometries are about the upper way. And in fact, the upper way, we could say it from the mouth or nose to the trachea. And the first one is maybe the simplest one of the USP model, and it used in some drug delivery. Maybe it's in the pharmacy industry, and in fact, it's not used so much now. Previously, people had do some research use it. And another one is that the middle one, I think, is a very good model. And this model is developed by the Finlay, that guy I just talked. This Canada professor Finlay, and this model is very famous for the upper way. And the third one is the realistic model. It was built from based on the CT scans. I think the first one is too simple, and the last one is too. It depends on the patients, and it's too subjective. Maybe for different people, it will have different geometry model. And the second one, maybe I think maybe it has some common properties of the people. But still, it has some problem. If you see the tricky, and tricky, you can see there's an angle here, but here is the angle is different. Yes, but still, this model is a good simplified model. And in fact, in the lower way, it can be called the branchial tree array. And for the branchial array, in fact, for R, you can see the long array. In fact, the earliest model is the Weber model, and the Weber model has 23rd generation, and in fact, people has used it a lot to build the segmented branchial arrays. For example, from J3 to J5, J7 to J9, J9 to J11, J11 to 40. And there are also other complex models. They use some complex model. They use a computer to generate ascending method to generate the branchial arrays. But they still have some what I say simplification, because they cannot. In fact, if we use the way of two branch method, it will have more branches, but the second, third, it don't have so many branchial arrays. So it still has some simplifications. And in fact, another one is that people. Yes, in fact, there's also some. In fact, my student asked my student to prepare this slide for me, but maybe I didn't put everything there. In fact, other than the branchial arrays, it's also the deep arrays. The deep arrays generally is from the 70 generations to the 23rd generations, and it's also called the Arvila regions. And then there's also some simplified models, because in the deeper way it's also very hard to get the real geometry is. And in fact, but if people try to get a whole array, because they will always want to get something close to the real world. And the first one is it was called the one-dimensional array, and it's from the mouse to the 23rd generation, and they simplified the long, and I think from the tricky brancher arrays, and also the array regions to one dimension tubes, and the second one also they combine the realist geometry model and the idealized array together to get a model from the mouse to the brancher arrays. And in this array, contains maybe some segmentation arrays, and also the long lobes. And it also considers the cartilage range here, cartilage range. Also this one. But this one is a little bit complex. It tends to from the generation 3 to the 23rd generation, and to the 23rd generation, and also this one is it has 5 branches. And anyway, and the people try to get a lot because the time is limited. Maybe I need to be a little bit faster. And anyway, people try to get a whole array, and this is I think the hot topic: how to get an array, and to this present the respiratory term. And the last one is our recent work. Yeah, maybe I will introduce a bit later. And also, I think in fact this model is developed by Professor Feng, and I think they have developed. I think we will also follow his way to from the larger branch arrays. We could use the 2-branch method, maybe to the 13th January, and from 40 to 23rd, we only develop for some branches in each tubes, but for the end of the arrays in the array regions, we don't. I think we will not use their method. I think their method is not so good. For the sec, it's not so good. Okay, and also people also consider the what I say is the glottis motion. Glottis motion, because the glottis is motion. I think for some maybe 10 years ago, when people do the simulation, they didn't consider the glottis motion, and also for the respiration, they think that the respiration flow rate is steady. It's just like a constant line, and this is dynamics. Yeah. And also, this is also part of our work, and we consider the yes, in fact we follow the work well, and then we do the simulation. We also, but we have successfully make to simulate the glottis motion. We use in the realistic model, and in fact in our work there's also still idealize the model somehow, because in the trachea it's idealized tube, but for us it's the realistic model. And in fact, this is much difficult to simulate the glottis motion. In the realistic model, it's more difficult to model the glottis motion in the realistic model than in the model of JAWS. In the JAWS model. And also in the alpha array, in fact, the flow is the R flow is it's controlled by the array. You can see that with a different array model, the flow is very different. For example, the flow in the side of the oral cavity, also in the pharynx and in the larynx, and then in fact, but one interesting that all of these R flow fate is different, but we could find a way to present the particle deposition with some particular parameter such as the Stokes number. Even the array is big different. The R flow is somehow different, but we still can get some similar deposition fraction. Yes. So and also for the tricky in the branch array, we could see that for different people, different geometry, and they may have different R flow fate. So in fact, we know that the R flow fate is very strong into subject variations. So it means that the R flow fate is very different among different people. And also for the whole array, and the people also say that in fact the flow is very fast in the upper array, and it becomes and also turbulent in the upper array, and then it translates. It's first is laminar, and then it will translate to the turbulent, and then it will become slow and become to laminar again. And even this, but in fact, one problem is that we don't know what's inside of the branch array, whether there's some strong, whether the flow is there, the turbulent is there strong in the thin arrays. From our research, we found that even with very thin, very fine array, there's still strong secondary flows, and also there's turbulence. There's turbulent and intensity is also strong. And in fact, we need to another question is we need to answer is that the turbulence why will be not turbulent in the array? Yes, there's there turbulence, but this is a problem is need to answered by the it need to be answered by the researcher in this community. Also, we say that people has found that the airflow impacts the what I say the airflow impacted by the lattice motion. The lattice motion impacts the vortex distribution, but in fact, but we need to know that for this work, they use the what I say the inspiration flow rate is the Sinner's curve. It's the Sinner's curve. It's not a realistic inspiration curve. In fact, recently we use some inspiration curve from the clinical measurements, and then yes, and this is also under the flow is under the glottis motion also impact the secondary distribution. Somehow it's you can see that there's a vortex here at this time 0.3, but there's no here, and from this vortex distribution, and also it can see that it in fact impacts the vortex distribution, and also for the particle deposition, I think in the upper area is mainly deposit it's by the flow impact, and it's mainly deposit in the where the airflow impact is on the airway, and for example here and here, and also but in the trachea it's maybe also because of the turbulence, because the particle has more, because the reverse the flow in the trachea, and then the particle will have more chance to stay here. And for the particle deposition in the bronchial tree, it finds light. The particle release position is it's highly related to the final positions. Our final positions are strongly correlated with their initial positions, and then the particles can go from the mouth throat to the to inside of the sac position, and then always also the glottis motion impact the particle deposition. And in fact, we have already know that the particle deposition has a U like this U curve in the upper airway and also in the whole airway. There's a U curve. It means that for larger particles, less than, because for too large particles, it cannot go inside or human respiratory tract, because it has a filter by our mouth and nose. But and for the particles less than 10, it can be go into inside of the respiratory system, and for the what I say, and only for this part of particles, they cannot deposition in the what I say, in the upper way, and but for the nasal particles, it also can deposit in the upper way. But for the particles between maybe 110 nanoparticle, 10 nanometers to maybe 3 micrometers, it cannot be easily deposited in the upper way, and then it can go inside to the lung. But for different, but in fact the deposition, the diffusion, the deposition mechanism is different. And for the small particles, for the fine particles, the deposition mechanism is different. And for large particles, for example, the micrometer particles, the deposition mechanism is impression and sedimentation. And then, and also for the particles, and we can use the Stokes number or impression parameters to describe to this is not just those number. It should be impatient parameters to describe the particle deposition fraction. And then, in fact, we all for the drug delivery area, we always try to make the particles to the special position. For example, to the factory position, and then we can use. In fact, we can use magnet force to control the particle to the olfactory. Then the particles can directly absorbed by the blood and by the nerve, and then go inside to the brain. And also we use this mechanism, and then use the then we can control the particles, drug particles released in the special site, and then it could go to inside to the geometry. Also, use this particle deposition properties. We also could analyze the risk and the particle when people takes the airplane and in the cabin. And in fact, the particle deposition areas is really depends on the depth, the comfort intensity, and the particle properties. And for different cases, it's different kind of curve. The deposition characters will be different. And also, this can be applied to the, for example, the working size, and people have to learn it to the wedding particles. How does they deposit in the human respiratory lung? And also, it's always depends on the people breathing density, the particle size. Yes, and also the also it's also depends on the gas change in the working site. Okay. And in fact, yes, and this in fact most work has done by others, and due to the time limit, maybe I introduce some our work. And in fact, this is, yes, for the simulation of CFD, and this is a typical case. The particles are released directly from the mouth inlet, and then it will go with the airflow, and then it's deposited on the airway. And then, in fact, for my PhD research work, I spent a lot of time to study the property of the airflow field. And in fact, we see that, in fact, I did a very detailed analysis. For example, I did analysis for the, yes, from this part is my research work mainly. And before it's the research work by others. And we did a very detailed analysis on the secondary vortex and the laryngeal jet and the recirculation zone. And in fact, it really depends. And these flow structures are very unsteady, and it really depends on the what I say, on the inspiration intensity. And in fact, what I'm interested in is the vortex, because the vortex is most important airflow structures. But it's a pity that after I graduated from my PhD, I didn't do some work to analyze how the vortex transports inside of the airway, and how the vortex interacting with the laryngeal jet, and how does it interaction with the recirculation zone. Because yes, and in fact, in the future, I'm president, I have a PhD student who has already published several papers, but he didn't, until now, he didn't did the research. I'm really interested in. For me, I really like him to do some analysis on the vortex dynamics, and it's also applied in the. It's not only my group. It's other group didn't do the vortex dynamic analysis, and I think the community should do some research in this area. And then yes, we also analyze these are structures, dynamics at different inspiration in cities. For example, 50, 30, and 60 city. And we have some small populations. Yes, and I don't go at the time limit. I don't go to so many details. And if you like, you can read my papers. And I also do because I did do some research work in the simplified geometry, and we also consider the deformation of the tree and how does it impact the flow. And we see that the deformation of the tree is mainly impacts the recirculation zone. You can see from these figures, the recirculation zone becomes small, but it's almost doesn't impact the larger jet. Yes. And we also consider because the glottis is very important for the flow in the trachea and the following and the flow in the downstream. Then first we consider different pressure shapes of the glottis and different concentration. For example, we consider two shapes, the circular and the elliptic shapes of the glottis, and with different production. And for example, the glottical area is 50% of the standard case and 95% of the standard case. We see that the reduction of the area mainly impact the larger jet intensity, but it doesn't impact so much on the on the shapes of the larger jet, but the shapes impact the larger jet much more, and also of course the glottis will impact the secondary vortex and the circulation zone. Yes, from these figures, and also the turbulent kinetic energy and the turbulent intensity. Yes. I also, in fact, I also tried to use the trumpet Holland do some analysis. And in fact, we found one big limited of its geometry in the diploma, because in fact there should be no vortex or so big a vortex or shear layer inside of the diploma. There should be laminar, even there may be some secondary vortex, but there should be not shear, just stress. Then I think this what I say, this whole RV model is not suitable to use it for whole RV model. And then in all of this trumpet model has been reported the first time that 2012, but afterwards almost no people to start to do research using this RV model. I think maybe because of this limited. And in fact, and then for us, the recent one of our recent research work is about the glottis dynamics, and we have modeled the glottis the glottis motion in the realistic model, geometry model based on CT scans. This is our model. This is our research work, and then and we also consider the what I say the realistic monolithic inspiration flow rate. In fact, we separate, we learn the flow rate considering the clouded motion separately for the respiratory phase. We do the research using the inspiration flow rate like first, and then we do the second part for the aspiration phase. And yeah, of course, I like it likes other people, and it's always find the glottis motion impact the flow. But I think but for our funding, this work was published in the POF. I'm sorry that in fact this work was done by one of my PhD students. Although I have helped him to revise the manuscript, but I'm not very familiar with the details. And but I think one of the big findings in our research work is that the inspiration is more important than the glottis motion. Always, but the glottis motion will definitely impact the flow rate, but it's not so strong as the glottis motion. Like the inspiration curve. We see that the pressure is also very unsteady because the inspiration flow rate changed, and it always has the similar profiles, and then the flow in the upper level is covered by three things. One is the inspiration flow profiles. And another one is the geometry structure. For example, it has this kind of profile because the complex geometry structure. And the third one is the glottis motion. But the glottis motion is not so important as the other factors. And in fact, why? Because, for example, the first one, the black one. In the black one, we consider both the unsteady inspiration, and we consider the glottis motion. And the second one, we doesn't consider. We assume that the glottis is staircase. We see the powder. The powder is only have a slight difference, but for the case one between the case 3, we were not case 2 and the case 4, they have different inspiration file, and the profile is different. It's so big a difference. And then it means that if we really want to learn the our pollution deposition in the inside of the inside the our RV, we need to use the realistic inspiration flow rate. And also for the powder, we can use one function to predict the powder. And this, in fact, I think this is fitting quite well. And also we analyze the what has structures, and we use the Q method, and we could say the Earth, the vortex structures is also related to the inspiration curve, because if we use the curve, it's increases first and then down decreases, and then in the larger the number, and it's more turbulence there, and with more turbulence, with a strong turbulence, it will has a more vortices. It's the same. It's the same thing. And also, we also did some SE analysis for the SE assays. We could see that the flow transmits from laminar to the turbulent, and then we see the laminar flow transits in the labyrinth region, and also in the tricky region, it may be transfers to the turbulence to laminar, and then transits back to turbulence, and then transfer to the laminar again. And always, in fact, always, if we don't consider the glottic motion, and we think that the inspiration flow rate is static. It's static. Then we will get less turbulent flow. And in fact, we also had some research work on the for the phase for the case of aspiration flow, and in fact, because the flow is and we also did a PSD analysis, and also the SE analysis, and the result is almost somehow similar. And we also consider the impact of the what I say, the respiration frequency. Due to the time limit, I will not end my research here, talk here. Maybe next time, in fact, we try to publish this recent part of work, and but it was rejected by many times. I think maybe in that work we talk too much on the relative field, and if there's an opportunity, next time I will introduce more on the research of tidal respiratory respiration. And in fact, also I will not talk this. And I think another thing I want to say is that, in fact, we always say particle transport and deposition, but in fact, in this research area, people didn't do sufficient research on the particle transport and deposition. And in fact, in most cases, people don't know how the particle dynamics inside of the array. And in fact, in my PhD study, I did do some analysis, and we say that the particles are significantly impacted by the vortex in the tricky, and then by the recirculation zone, and then the particles has more time to stay in the inside the tricky. And in fact, we also did some application studies. For example, we study how the temperature may influence the various particles deposition inside of the array, and then we say that, in fact, the temperature has, in fact, if the temperature is too hot and too cold, definitely it will impact the particle deposition. Yes, and then also we we studied the cough jet somehow, but this work was with concurrence. And we say that we compared our simulation with with the experimental study, and we say there's some, it's almost close, yes, somehow, but maybe here is I think the inside here is okay, but here maybe need to do more work, and I think here is somehow different between our simulation and the experimental. And we also try to study the case when people has mask, has the main word, when people wears the face mask. And we see that if we people wears the face mask, in fact, he doesn't reduce the risk. And in fact, he changed the risk. And maybe if the people wears the face mask, and in fact, it's more dangerous in the back of the people, not in the front. But if the people doesn't wear the face mask, then it's more dangerous in the front side of the people. And then the mask also, you can see it's change the distribution of the cover jet particles, the aerosols from the cover jet. And we also see that the surrounding flow and the injection positions for the drugs, and in fact, it will definitely impact the delivery efficiency. And it's always could do some what I say. We could change the parameters to enhance the delivery efficiency and try to find a better to improve the drug delivery. Use suitable parameters, and also this is the psych. It's capsular sex, which can help to enhance the delivery drug delivery efficiency when for the active dry powder inhaler. Yes, in fact, this work was collaborated by me and Iran researcher, and also this one, and also the last one as well. And this is we did some also for the humility. But yes, yes, this is, sorry, I forgot this work because it's so long time ago. And yes, I'm sorry. Maybe it takes too long time. It's expected. And I would like to summarize my research work a little bit. In fact, we did in this part of work, we try to learn the physics of the airflow dynamics in the human respiratory human respiratory system, and we try to use a whole array. And in this array, whole array, it will consider as many branch arrays as possible. And we also want to consider consider the lattice motion, and in the future, we'll also consider the heat transfer. And then we want to get the realistic case, the air pollution particle deposition in the array. And then, in fact, we are also doing some work to use more suitable models to describe particles. We want to do some research on the irregular shapes of the particles. And then we will consider more, as I said, consider more on the physical characteristics, and we also want to use the whole array, and we will also use trying to plan to use some better large array simulation models, and as well use some more advanced particle models. This is some of my research work, and thank you for listening. Alex, and in the end, I like to thank the financial support from DFK and from Chinese government. Hello. Alex.
Yeah, I'm
Alex.
here.
Oh,
Thank you.
yeah. I'm sorry, maybe my English is not so good. And I didn't, yes, maybe, yeah. Do you have more questions?
Yeah, questions, please. Is any questions from the audience? You can write in chat, or you can ask.
Yeah, maybe it's better to write. Maybe better for you to write your question.
But it's better to write your question in chat. So
yes,
if it's possible, yeah. So when people is okay.
抱歉，我在这给他们做报告，可能还有10分钟。Okay. If you have a question, you also can send me an email. In fact, I'm sorry. Maybe we could have a chat a little bit, and then I have a meeting later. So, Alex, maybe we could chat privately for some minutes. Yeah,
okay,
maybe you can take other people also yes away. It seems that is there a question?
So I've got some questions, if it's possible. Yeah.
Oh yeah. Oh, okay. If you have questions, it's fine for me.
Yeah. 3 small questions. So you talk about in the beginning of your presentation about wall shear stress. Yeah.
Yeah.
So you showed some slides. Yeah. And I know that in blood flow mechanics, wall shear stress, they are used to characterize the possibility of atherosclerosis formation in blood. But how this indicator, this feature is used in respiratory mechanics? What this parameter characterizes in the field of
yes, I think for the WPS it's only I think that in fact for it's mainly use the USA, the OSA. I'm sorry, I forgot the whole something. Yes, and this is yes, and in fact people who don't use it quite a lot. It's only for this kind of disease. And they will say that if it's big or if it's too big, and they think that this structure is not steady. It's easy to collapse. Yes.
Okay. So which I didn't maybe I missed that. Which turbulence model do you use?
The model I use large array simulation model.
SST.
Not. I think a large array simulation. RES.
Less. Okay, large array simulation. But Yeah.
And in fact, I also use Rand's K model, K omega, K omega model.
Okay, but which is good? How do you feel? How do you feel, for example, comparing with SST model?
I think a large ID simulation is better. Yes, I think I always think a large ID simulation is better than SST omega. And in fact, a large ID simulation, it may take more time, small steps, time steps, but it's always better. It's always quite better results because it could get care of what has. Yes, I think RES is better.
Okay, but maybe you can lose something when you use large eddy simulation. You think you put this kind of cell, and you can lose maybe small flows, and maybe it would also make some effect.
Yeah, well, I don't think so. I think a larger animation always contact small scale model, small scales. But maybe I think but it's up to what I say, up to the what kind of the flow is. Maybe there's some only turbulence. If the turbulence is strong, they are fully developed, then I guess the T is okay. In fact, but I think what I say, the shortage of the larger eddy simulation, it takes more time. I think this is it cost the resources. It is quite huge resources. I think this is the shortage of larger ID simulation. Yes.
Okay. Okay. I got it. So, and my last.
Okay, thank you.
Okay, my last.
This is in fact for the evaporate droplets.
So my last questions is about turbulent kinetic energy and turbulence density. So can you please also mention a little bit, talk about how can this characteristics like turbulence kinetic energy and turbulence intensity, for example, used in medicine for some kind of diagnostics maybe, or something like that. Why do we need to calculate this kind of parameters?
I'm sorry. In fact, I don't. I think for me, why is the problem is light. We don't know. I don't know. I didn't connect with my research to the kinetics. I don't know it. In fact, I don't know. I think it's only light because my background is fluid mechanics. And my background is a fluid mechanics, and it's always important to know the turbulent kinetic energy and the turbulent intensity. But how we use it, I'm sorry, I don't know it. But maybe in the future, we could think about it. For example, maybe we could think about it. We can measure the turbulence. We could measure the turbulence intensity, and then we connect with CFD. But for example, asthma. But maybe we could use AI method. Yes, use the machine learning or artificial intelligence, because with CFD we could get some parameters, And then we need to, if we also know some from the clinic applications, we know some people they have some disease, and then we connect these parameters and then to the people who has the disease, then maybe we could use it. Yeah.
Okay, we have one person who wants to ask you personally, and we have two questions in chat. And I think that we can first give opportunity to ask you personally, and after that, we will come back to chat. Okay?
Okay.
Yes, you can ask.
Yeah. Well, yes. I think that first I answer these two questions. Is it right?
No, Professor Deshevsky, I don't know. Can you hear?
Yeah, I think.
Okay.
Yeah.
So
the
first question in chat. What can you tell on the simulation of evaporated droplets?
I think for the we say that for the and we in fact we in one of our work that published in the R, and another one published in the sense of total environment, and in that part of work we consider the droplet evaporation, and we say that for the droplet will be evaporation faster if the environmental temperature is high, and also if it's the humidity is low, and then after the droplet evaporates, and then what I say, and then it will become smaller, and the size will become smaller. Then it can be transported for a little bit far. So it means that in fact the virus in the hotter and dry environment are could transport faster. Yeah, and this is my answer for the first question. And the second one is what's the boundary conditions?
Do you set
for the boundary conditions in the okay. Moment.
Yeah, too many questions. Yeah.
I have answered the first question, and for the second question, and for the boundary questions, in fact, on the inlet, in fact, there's two kind of boundary conditions. One is assumes that it's a steady inspiration flow rate. So it seems like you assume that the velocity is only have one value. For example, it's only 50 liter per minute, and this is one kind. Another kind is like the unsteady. The unsteady flow rate is like a curve, and we use both of them. And for some cases, if we want to learn the theory, then we use the second one. We want to use it more realistic models. But if we do some projects and we want to get the faster results, then we use the steady conditions. And what I say for the steady conditions, and then what I say, and for the pressure that's the inlet. We assume that the pressure is the same as the ambient environment. It's like 1.01, like the 100,000 Pascal. And for the outlet, we just say that it's the flow, the airflow just flow out it. We don't give the specific velocity. But in fact, some people give some also give the pressure and also in that outlet. But in fact, it's also a problem. How do we give a suitable boundary that's the outlet? And this is the second question. And the third question is like, yeah, for the deformation of the wall, we didn't use the fluid structure interaction method. We didn't use the FSI. We use the dynamic grid method. We use the dynamic grid method in open form. We use the open form, and for the glottis motion, we use the dynamic grid method. Maybe in the future, we will use the FSI method. Yeah, because I will use the open form, and my students use the open form, and then maybe one of my students, maybe I will in the future, if I have more students, maybe we'll use FS method. And last question is like,
are you in touch with doctors?
Yes, I have some of friends from doctors, and I also have some conversations. I got some medical image from them, but I'm sorry, they didn't use my method. As I just said, like I don't know how to use my results, and maybe because now I try to do some theoretical research. I want to have more populations, and now I'm only associate professor. After I got my full professor position, I will do some research for the application and to get more money. So thank you. This is all my answers. Yeah.
Yeah. Okay. I guess that we need to finish this seminar. Once again,
Yes.
thank you very much for opportunity to make a presentation. Yes,
Thank you again.
We really appreciate this. Thank you.
Yeah, you're welcome. Yeah.
And I've got small announcement for our audience. I will switch in Russian because we have Russian audience. I would tell some words in Russian. Уважаемые коллеги, всем спасибо большое за участие. И увидимся через 2 недели. На следующей неделе семинара не будет. Так что через 2 недели, 18 числа, я думаю, что мы с вами увидимся. Всем всего